In this video, we'll first cover differences between relational and document databases, how they store data, and when you should choose one over the other. Then we'll discuss how you can use Postgres as document-oriented database, what data types are available to you, and which one you should choose and compare their performance. We'll also cover some indexes that you can use to significantly improve performance of your queries when working with JSON documents. For example, in this case, when I create index, it significantly decreases the latency for those types of queries. And of course, we'll run a benchmark using common use case for e-commerce website. So in this case, we'll measure latency for insert, update, delete, as well as select operations in both Postgres using JSONB data format and MongoDB. We'll also measure how many queries per second each database can handle, and we'll look at CPU usage for each database, disk write operations per second, as well as disk usage. We'll also cover some features that only MongoDB can perform with JSON documents. For example, you can join multiple collections and aggregate data to find the total amount sold of each product. Now, I run all my tests in different public clouds. In this case, I used AWS and specialized i3en large EC2 instances for the databases. I've also set up EKS cluster with Graviton instances to deploy my monitoring components like Prometheus and Grafana. And I use Kubernetes job to deploy clients to generate load. To support my channel and cover the costs of AWS and other cloud services, I would like to offer one-on-one sessions. You can find more information about this in the video description. Let's say you have a table where you store all the products purchased by your customers. It's just one big single table where you have the product name, its price, and how many of these items your customer bought. Since it's a single table, you would store your customer information right beside it. For example, if you have a single customer who bought all those products, for the customer, you might have their name, address, and phone number. If you want to fetch any particular order, you would use a similar SQL query. Now, let's say your customer has changed their address and you need to update every single database record for that customer. You can do this with a similar SQL query. If you only have a few orders and customers, it's fine, but if you have thousands, it can quickly add extra load to your database and slow it down. Another problem is that when your customer makes a new purchase, you need to copy all the data over and over again. So how can you solve this problem? Well, we can create another table. Let's call it customer. It would have ID, customer name, address, and phone number. Now, we set primary keys on these two tables. A primary key is something that uniquely identifies a record in your table. So each customer would have a unique number associated with them. In our main table, we can now replace all that customer data with a single ID column. That ID is called a foreign key, and it's just a way to establish a relationship with the other table's primary key. So now, if you want to get any specific order, we need to join those two tables using the foreign key. This time, if the customer changed their address or phone number, you only need to update that piece of information in one place, and all orders will be automatically updated when you join them again. Also, we don't need to copy all that customer information over and over again. We just use a single small number, which also reduces the storage needs for our database. Let's optimize it a bit more. Let's create another table called product. We'll use the same columns. We would have a primary key for the product, its name and the price. Now, let's remove all that product information from our main table and use a foreign key for the product as well. Now, if you want to get a specific order, you would use the following join to combine all three tables. So this is the main idea behind a relational database. You create different tables and use primary and foreign keys to join them together. Now, let's say you have e-commerce website that sells all kinds of products. For example, you might have a similar columns: ID, the name of the product, the price, and maybe ingredients column for the shampoo products. Now, let's say you decide to sell leather jackets as well. You would have a name and price, but this item doesn't have ingredients. You would use null for that column, but this item might have additional attributes that shampoo products don't have. So in this case, you would need to add another column to your table to indicate the size of the jacket. In a few months, you decide to sell monitors. So you would use nulls for the irrelevant columns, and you can see where I'm going with this. So the more products you add with different attributes, the more columns you need to add, and most of them will be empty because they are not relevant to most products. This is a case where you need a flexible database schema, which relational databases don't really provide. What you can do is to use a document-oriented database and store each product with its own set of keys. That way, you don't need to include irrelevant attributes for each product. Now, if you decide to use Postgres to store JSON, you've got two options. You can go with JSON data type, which is text-based. It keeps white spaces and the order of the keys in your JSON document. On the flip side, there is JSONB, which uses a binary format based on JSON. It's much smaller, queries run more efficiently, and it supports indexes, making your life a lot easier when working with JSON. From these two graphs, you can see that it takes pretty much the same amount of time to insert both JSON and JSONB documents. But if you're planning to do anything like search by specific keys or updates, JSONB is much more efficient. On the top window, we have Postgres shell, and on the bottom window, we have MongoDB shell. I just want to walk you through the queries I'm going to run in this test. First, we still need to create a table for the Postgres. We'll use ID column and JDoc column of type JSONB to store JSON documents. Also, your go-to index is Gen. You'll find yourself using it the most if you have many documents with different keys, and you need to search using specific ones. On the other hand, MongoDB automatically creates collections and index for the ID column, which we'll use later. But we still need to create index for the price column because we're going to use it in our select query. Next, we're going to insert a few products into each database. Then we'll update the stock value of one of the products we inserted. After that, we'll search for products that have a price under $30. And finally, we'll delete one of the products we inserted by its ID. So this is the test we're going to run. When you're working with JSON in Postgres, most of the time you would create a gin index on the JSON column in your database. This index gives you a few more operators that you can use to query your JSON fields. On the other hand, don't forget to create indexes in MongoDB as well. For example, when I create index on this field in MongoDB, it will immediately improve your query performance, even with a small amount of data. So keep this in mind that indexes play a huge role in MongoDB to improve performance of your specific queries. The last thing I want to mention is that MongoDB has many more features specific to JSON documents. For example, you can join multiple collections and query them both, similar to performing outer left join in SQL database. Let's say on the top window we have a Postgres shell, but now we're dealing with a relational model. We've got order table and inventory table using the following columns and establishing a relationship based on this foreign key. Now, you can create a sales view by joining these two tables like this. This is a left outer join. Next, you can run the following query to find the total amount sold of each product. You don't have to create a view. It's just a way to reuse the same query without explicitly running it again. On the MongoDB side, let's say we have the same inventory collection and order collection. We can create a view here too, like this. We use foreign keys here as well, but they are not enforced in MongoDB. Then use the following query to find the total amount sold of each product, but this time in MongoDB. This functionality is only available for querying JSON in MongoDB and not in Postgres if you use JSON data type. Alright, let's go ahead and start the test. In this video, we'll measure latency using P90 percentile. You can think of P90 as the point where 90% of all requests completed within the time range shown on the graph. I'm using P90 instead of P99 to reduce the noise. With a lower percentile, you have fewer spikes. On the right side of your screen, you'll see the number of queries per second that each database receives. On the left, we have the latency for insert, update, delete, and select operations. For the first 10 or 20 minutes, while both databases don't have a lot of load, you can see that the latency is very similar except for the select statement. However, this will change as we start to increase the number of virtual clients sending those queries. For this test, I used a dedicated disk for the storage for both databases, which I mounted to /data directory, and I measured the number of write disk operations under that directory. So the biggest difference is in disk write operations. It's very consistent across other tests I've run, like with MySQL or SQLite. Postgres always performs many more disk operations compared to any other database I've compared with. If you know the reason, please let me know. We also measure CPU usage for both databases, and it looks like MongoDB performs a little bit better. And we also have disk usage for the data stored on the local file system. At around 3500 queries per second, you can start to notice latency spikes on the Postgres side, which are most of the time associated, or I would say probably caused, by Postgres storing data on the disk. If you watch the disk usage carefully, most increases in data volume associated with those latency spikes, as well as CPU spikes. At around 6000 queries per second, Postgres starts to drop more and more requests and falls behind MongoDB. The higher the usage of Postgres, the higher the latency spikes become when it writes data to the disk. At around 8000 queries per second, Postgres completely falls behind and has much higher latency compared to MongoDB. Now let's go ahead and run a test for a few more minutes until both databases reach full CPU usage. So this is pretty much the maximum number of queries MongoDB can handle as well. Let me open each graph for the entire test duration. First, we have queries per second. Up until 5000 queries per second, Postgres still handles requests very well, but shortly after, it fails. MongoDB, on the other hand, was able to handle almost 13,000 queries per second. Then, let's take a look at the insert latency. Up until 5000 queries per second, it holds fine, but after that, latency increases significantly. And the trend pretty much is the same for all other database operations. Here we have update latency, delete latency, and finally select latency. Now, let's take a look at the disk write operations per second. You can see there is a huge difference here, and if you can explain this, please let me know. Then we have CPU usage for both databases, which converge pretty much at the same time. And finally, we have disk usage. You can see a slightly different pattern in how both these databases write and store data on disk. So if you already have a Postgres database and want to use it as a flexible document store, it's possible, but JSON for Postgres is not a native format, so you might use it as a temporary storage and then move to specialized document database like MongoDB. MongoDB, on the other hand, has many more features related to JSON objects. So if you know you'll primarily be working with JSON objects, I would highly suggest starting with MongoDB in the first place. It's also easier to scale horizontally. I have other benchmarks on my channel that you might find interesting. Thank you for watching, and I'll see you in the next video.